Welcome to the Picture Language Seminar. We have a special guest here today, David Ruel, who's visiting from Paris. And David is sitting next to me. He's going to give the historical lecture this afternoon about the history of physics, the David Lee lecture. And on Thursday morning at 9:30, we'll have a special seminar with David. But today, we're very, very happy to have Eddie Frenkel. Eddie was one of the first Russian prize fellows in 1989 at Harvard. So at the time, I was head of the mathematics department, and was a great pleasure to be able to welcome several guests from the former Soviet Union. So Eddie's going to talk about the Analytic Langlands correspondence for complex curves. Eddie, why don't you share your screen?
All right. Can you see it well?
Perfect.
All right. Well, first of all, I would like to thank Arthur for his invitation. Arthur has played a great, an important role in my career and in my personal life. As he just mentioned, in 1989, I received an invitation to come to Harvard University. I was just barely 21 years old, and still in my last year of undergraduate studies in Moscow. And suddenly I receive in my mail a letter from the president of Harvard University, who at that time was Derek Bok, inviting me as a Harvard Prize Fellow to visit Harvard for a semester in 1989. So needless to say, I was very surprised. Well, I had done some work before that on actually some of it I will mention here today with Boris Feigin in Moscow, and I guess that work kind of became known and led to this invitation. Still, I later realized it was Arthur who was instrumental in putting me on the list of the first Harvard Prize Fellows and actually creating this fellowship with some support from Israel Gelfand, I understand. And so there were three of us, Nikolai Rishtichin, Boris Tsigan, and myself. And so I remember very well, in September of 1989, I arrived in Cambridge, Massachusetts from Moscow. And so Arthur sent one of his graduate students to pick me up at Logan. But the next day, he actually paid a visit to me at the apartment at the Botanical Gardens, where I was staying, again, arranged by Arthur in the math department. And he was so generous to come and to pick me up and to give me a tour of Cambridge, Massachusetts. So, it was super cool. I was 21 years old and, being, driven by one of the greatest, mathematical physicists in the world. So it's like, wow. And then he said, well, do you need to buy anything? And I needed salt in my apartment. And so he took me to Star Market on Porter Square, which was the very first time that I entered a supermarket. In those days in Moscow, there were shortages of food. And here I saw the abundance of everything. And I guess I was kind of mesmerized by it. So I basically was just walking around the aisles for 45 minutes, unable to find anything. So finally I found something and came out. Arthur was bewildered. What's going on in there? So, this story, by the way, is now available in 19 languages because I recount it in my book, Love and Math, and as well as the story behind all of this. So anyway, this is just to say how long and how important this connection is to me. And I would say that if anyone else asked me to give this seminar at 6:30 in the morning, which is what time it is right now in Berkeley Hills, I would probably find an excuse. But in the case of Arthur, I could not say no, for better or for worse, as we will now see. So after this introduction, let me get to the subject matter. Today, I would like to talk about analytic Langlands correspondence for complex curves. And this is actually a joint work with Pavel Etingof and David Kazhdan. David Kazhdan, by the way, was a professor at Harvard at the time, and he was one of the people with whom I spent a long times, talking and discussing mathematics and learning from. So again, this is kind of a long connection as well. And Pavel was my classmate in Moscow. So it's kind of this collaboration is also kind of goes back to those special days. We have now 3 papers on this subject, which I have listed here. You can find them on the arXiv. And this work, I must say, also was motivated by a suggestion of Robert Langlands himself, as well as results of Jörg Teschner. And in this work, we propose a new version of the Langlands correspondence for complex curves, which we call Analytic Langlands correspondence. I would like to start by giving a brief outline of what this Langlands program is about. In the late 1960s, Robert Langlands launched what has become known as the Langlands program. And its goal was to relate some deep questions, seemingly intractable questions in number theory, to some more easily solvable questions in harmonic analysis. In particular, Langlands conjectured that Galois representations of Galois groups of certain fields, which I will talk about more precisely on the next slide, and motifs can be related to what's called automorphic representations. And through this correspondence, some intricate and subtle number theoretic data associated to Galois representations can actually be obtained from much more easily discernible analytic data, which come from the automorphic representations. Here is Robert Langlands at his office at the Institute for Advanced Study. The picture was taken in 1999. He still occupies the same office, which was in the past occupied, but no one else but Albert Einstein. It's a very nice office, I must say. And here's a cover page of a letter that Langlands wrote to another giant, André Weil, in 1967. That was the letter in which he formulated the first version of some of his conjectures. This letter is kept at the Institute for Advanced Study in the archives. And you might be able, maybe it's difficult to read, so I'll just read it for you. Professor Weil, he says, in response to your invitation to come and talk, I wrote the enclosed letter. After I wrote it, I realized there was hardly a statement in it of which I was certain. If you're willing to read it as pure speculation, I would appreciate that. If not, I'm sure you have a wastebasket handy. A kind of an understatement of the century. So in this letter and then subsequent work, Langlands formulated his first conjectures. I want to give an example of the Langlands correspondence. A special case is the celebrated Shimura-Taniyama-Wei conjecture, or sometimes known also as modularity conjecture, which is extremely important in number theory. It states that information about two-dimensional Galois representations. So it's a special case where one considers two-dimensional Galois representations, which come from elliptic curves over the field of rational numbers. They basically come through what's called the first étal cohomology. If you think of an elliptic curve over the field of complex numbers, it is just a Riemann surface, and as a surface, it's just a torus. So its first cohomology, just ordinary cohomology, is two-dimensional. In the number theoretic situation, one has an analog of the kind of topological or the Ram cohomology, which is known as the étal cohomology. And the first étal cohomology of an elliptic curve over the rationals is also two-dimensional. It affords a two-dimensional Galois representation of the field of rational numbers. And when I say information about this representation for a given elliptic curve, it really boils down to knowing how many points this curve has when we reduce it modulo a given prime. So imagine trying to find out the number of solutions of a certain equation, algebraic equation, which gives rise to this elliptic curve, modulo primes. It's an equation over the integers. You can write it as an equation over the integers, so you can reduce modulo prime. Try to find out numbers of solutions is a very difficult task, and those numbers, they kind of look completely random. Yet it turns out, and that's the statement of Shimura-Taniyama-Wei conjecture, that all of them can be found at once as coefficients of in sort of q to the power p of a specific modular form, an analytic function on the upper half plane. Finding those coefficients, needless to say, is a much easier task. And that's why it appears as a kind of a miracle that suddenly you can convert something that seems to be very random and chaotic and difficult to find into something much more regular and easily discernible. In 1995, Andrew Wiles and Richard Taylor proved this conjecture in the semi-stable case by a theorem of Ken Ribet, one of my colleagues here in Berkeley. This implies Fermat's last theorem. And this is just one small special case of the Langlands program, of the Langlands correspondence. In fact, there is much more. The Langlands correspondence can be formulated in 3 different scenarios. André Weil wrote a famous letter to his sister, Simone Weil, in 1940, while being imprisoned in France for refusing to serve in the army during the war. And in that famous letter, André Weil talks about a kind of a Rosetta Stone of 3 fields of mathematics which are intricately connected. The first one has to do with number fields. The second one with curves over finite fields. And the third one curves over the field of complex numbers, which are also geometrically Riemann surfaces. So let me briefly talk about this. Before I get to this, so there are 3 columns of the Langlands program. There are 3 different formulations, or 3 different flavors, if you will, in the framework of André Weil's Rosetta Stone. But actually, in the last 15 years or so, a 4th formulation has emerged, which actually has to do with quantum physics, more specifically S-duality or electromagnetic duality of 4-dimensional supersymmetric gauge theories, also linked to what's called mirror symmetry in 2-dimensional quantum field theory. And this work was initiated by physicists Kapustin and Witten, who linked S-duality to the Langlands correspondence for curves over the field of complex numbers, the geometric categorical Langlands correspondence. And this has inspired a great deal of research in this area. More recently, just in the last, in the past year, Gayotto and Witten have given an S-duality interpretation and brain quantization interpretation of some of the results in the analytic Langlands correspondence that I'm going to talk about today. So now there is a 4th story which kind of runs in parallel to the 3 mathematical stories. The 4th story being physics story, running in parallel with the 3 mathematical stories that I mentioned in the previous slide. Now let me explain a little bit more detail what I mean by those 3 columns, 3 scenarios of the Langlands correspondence. The first one has to do with number fields. And by number field, we understand finite extensions of the field of rational numbers, obtained by adjoining to the field of rational numbers, roots of polynomials in one variable with rational coefficients. Next, we consider a curve, an algebraic curve over the field FQ, the field, a finite field with Q elements, where Q is a power of a prime. And given such a curve, we can look at its field of rational functions. For instance, if the curve itself is a projective line, P1 over the field FQ, then this field consists of all fractions, ratios, P of t divided by Q of t, where P and Q are 2 relatively prime polynomials in one variable with coefficients in FQ, with Q of t obviously being non-zero. So they look very similar, like very similar to rational numbers, which are also fractions, P over Q, where P and Q are integers, relatively prime integers. And such a field is called a function field. And so as you see, there are a lot of analogies between number fields and function fields of such curves over finite field. So these are the first 2 columns of the, remember, there are 3 columns or 3 scenarios: number fields, curves over finite fields, and curves over C. So we have just discussed the first one and the second one. And the third, we consider function fields of curves over the field of complex numbers. So in the case of a projective line, for instance, over the field of complex numbers, that would mean that we consider the field which consists of fractions P of t divided by Q of t, where P and Q are now polynomials in one variable, but with coefficients in the field of complex numbers. So needless to say, they are similar to each other as well, the function fields of curves over FQ and over the field of complex numbers. The idea of André Weil. So André Weil did not think in terms of Langlands program. This is 1940. Remember that he proposed this type of this sort of overarching analogy. His idea was that a lot of results in this column have counterparts in this column and then counterparts in this column. And he used this idea to search for new results. And one of the greatest discoveries that he made in this process was the discovery of Ital cohomologies, which was an idea that you could use try to transport the notion of cohomologies for curves over complex numbers to curves over finite fields. But then this led him to the definition of zeta function and then an analog of the Riemann hypothesis here, which became known as the Weil conjecture, or actually the number of Weil conjectures, which greatly stimulated the development of mathematics in the last 70 years, 80 years. Okay, so that was his idea. But it turns out that the Langlands program is well understood in this framework, that there is a Langlands correspondence in this column, there is a Langlands correspondence in this column, there is a Langlands correspondence in this column. And again, they are slightly different, but there are also many commonalities between them. And we use these analogies to be able to guess new results, to guess new, to develop new tools and so on. Initially, the idea is to understand some deep results for number fields like Shimura-Taniyama-Weil conjecture, but they're difficult. So we then move this into this realm where some of the things are more clearly seen, more clearly visible, where we have tools which are still yet unavailable here, and so on. Then move over here and try to find some results here and then go back. In the last 20 years, a lot of progress has been made in this way. And now we have a fourth, we have a new help from physicists, we have a new column here. So we can also learn some tricks from physicists and try to transport them to this column, and then hopefully here, you see, to get some new results, get some new ideas. That's how the subject has been developing in the past 50 years. But let me say what exactly this correspondence is. Now, the first two columns are very similar. And in fact, those two columns appeared in the original formulation of Langlands, you see. The third column came later, and it is kind of different. It's very different from the first two. At least that's how we thought about it until recently. So let me talk about the first columns, number fields and function fields for curves over a finite field. The two realms of the original Langlands formulation. Because they're so close, it will be convenient for me to just focus on the function fields for curves over a finite field. In this case, one example is the Langlands correspondence for GLN. And I will just talk about the what's called the unramified version. It doesn't matter at this point what this means, kind of a simplified part of it. It is actually not a conjecture anymore. It is a theorem. In the case of n equal 2, GL2, it was proved by Vladimir Drinfeld in the 80s. And then Laurent Laforgue was able to generalize his approach for all n. Both of them received Fields medals for this work. So this is really considered as one of the milestones in the subject. The Langlands correspondence sets up a correspondence between objects of two very different type. One has to do with Galois representations, just like I mentioned earlier, and the other with harmonic analysis. Specifically, we are considering representations of the Galois group of this field, n-dimensional representation. So it's an n-dimensional representation is a homomorphism to GLN, right? Unramified in a certain sense. And so the Galois group is just a group of automorphisms of the algebraic closure of F. And F is a function field of a curve over a finite field, right? Which preserves the original field. On the other hand, we consider this group GLN over what's called the ring of Adels. Perhaps it's not so important what it is, but I wrote a definition. It's a product of what's called restricted product of completions of this field, which are basic. Each of them is like a field of Laurent power series in some local coordinate at a given point. And these are the Taylor series. So we have this group and two subgroups, and we take a quotient, and there are certain operators acting on functions on this space, and we consider eigenfunctions of this operator. So these are the objects of harmonic analysis. They are the close cousins of for instance, modular forms on the upper half plane, which appear in the number theoretic column of the Langlands correspondence. And so, lo and behold, there is actually one-to-one correspondence between the two. And not just the one-to-one correspondence between two infinite sets, but actually there is more structure. These homomorphisms have some invariants attached to them, and these Hecke eigenfunctions also have invariants attached to them, namely eigenvalues. And it turns out that under this bijection, this data match, data on the left-hand side and on the right-hand side. And that is the beauty of it, so that you can discern, you can find out information about Galois representations from some data of harmonic analysis, you see. So that's the idea. But there is more. And so there is this twist in the story, which is sort of one of the most fascinating aspects of it, in my opinion. If we replace GLN, so you see, there is GLN on both sides here. Here's GLN, here's GLN. What if we replace this GLN by some algebraic group G, like even say SLN or orthogonal group or symplectic group? What's going to happen? Can they also be matched on, to some data associated to Galois representations? It turns out that yes, but the group which will appear on the left-hand side will be different from the group which appears on the right-hand side. If the group on the right-hand side is called G, then the group on the left-hand side will be a different group, which became known as the Langlands dual group of G. Here are some examples. GLN is self-dual, and so that's why at the level of GLN, we don't see this subtlety. But SLN, for instance, already is not dual to itself, but its dual is PGLN. Symplectic group is dual to the orthogonal. Spin group, for instance, is dual to SO2N over Z2. And E8 is self-dual. E8 is in some sense the simplest simply group from this perspective. So, and likewise for every reductive algebraic group, G, we can associate its Langlands dual, and still we have a correspondence between Hecke eigenfunctions on this double quotient and homomorphisms from the Galois group of F to the Langlands dual. Now, here's a key point, which actually is due to André Weil. As you see, André Weil is kind of a very much an important character in this story. Not only he was on the receiving end of that famous letter from Langlands, but also we are talking about the Rosetta Stone analogy, which is due to him, but also this very important result, which allows us to connect everything to geometry. So the result is the following: that this double quotient that I talked about, which appears in this correspondence, where this is where Hecke eigenfunctions live. They're functions on this double quotient. It actually has a nice geometric interpretation as a set of equivalence classes of G bundles, principal G bundles on the curve X, you see. So it's very nice. We call this bond G of FQ. This is a set of equivalence classes of G bundles. So the Hecke eigenfunctions, the objects on the right-hand side of the Langlands correspondence, actually live on something that it has geometric meaning. It is a set of equivalence classes of G bundles on X. And so here I left some space to draw a picture for you. You see, there is just to outline this argument, why this double quotient is indeed in bijection with a set of equivalence classes on X. Now, I need to draw a curve over a finite field. That's not an easy task. So instead, I will draw a curve over complex field, you see, so which is a kind of a Riemann surface like this. It maybe has two holes. So how to describe a principal G bundle? Let's say G is a group of SLN. How to describe a principal G bundle on this Riemann surface, so that X, but now it's over complex numbers. However, the argument for complex numbers and for the finite field is essentially the same. The idea is to use transition functions. It turns out that every such bundle can be trivialized in a complement of finitely many points. So we pick some finitely many points, and so we have the set X without those points. Let's say X1 to the Xn, and so the bundle can be trivialized on this open subset, and the bundle can also be trivialized on small disks around these points, right? Now, if we have a principal G bundle, so we know it can be trivialized on this subset and this subset, then it can be described by transition functions. By you have to identify the two bundles on the intersection of the two open subsets. This intersection is going to be union of punctured disks, right? So the intersection between this set and the union of these disks is going to be the union of punctured disks. And so every so a transition function just corresponds to a collection of G-valued functions on punctured disks. But that's exactly an element of this adelic group. And if we change trivializations, the bundle stays the same, but we can change trivializations in the complement of these points and on those disks, right? And that's exactly taking the quotient by these two subgroups. So that's how you relate equivalence classes of G bundles on X to this double quotient. And this works equally well for curves over FQ and C, but the formulations are very different. If the curve is over a finite field, then this set of bundles is actually a discrete countable set, and it has a natural measure, which assigns to every equivalence class 1 divided by the group photomorphisms of this bundle. This is well defined because now everything is over a finite field, and all of these groups are finite. So this makes sense. I mean, it would, even if it's infinite, it would make sense, but it kind of it would be attaching 0. So that would indicate that something is not quite right. But here they're all going to be rational numbers. The measure is just a collection of these numbers attached to each equivalence class, and they're only discrete countable set of classes. So once we have this measure, which is, by the way, can also be defined in the adelic language. I'm defining it in the geometric language of bundles by using this Andrei Weiss result, but could also be defined in terms of the adelic groups themselves. And in that formulation, this measure is known as the Tamagawa measure. Once we have that, we can define the Hilbert space, namely just take the square integrable complex value functions on this set with respect to this measure. And then it is equipped with a standard Hermitian inner product, which is just you have this infinite sum of this values of this. You have two functions with their values at each equivalence class. They're both square integrable, so this converges, and we get a well-defined Hermitian inner product. That's our Hilbert space. And so the Langlands correspondence for curves over a finite field can be formulated in terms of this Hilbert space. You see, so on the automorphic side, so remember, the way I first stated it for GLN or for general group is that you have this right-hand side. That's what I call automorphic side. And this you could say it's Galois side. So on the automorphic side, you have functions on this double quotient, but now we have interpreted this double quotient as this set of equivalence classes. And when I say functions, what kind of functions? Actually, what I mean more specifically is the Hilbert space of square integrable functions with respect to this measure, right? So next, you have some self-adjoint operators, mutually commuting self-adjoint operators, a collection of operators labeled by points of the curve and some what's called dominant integral weights of the Langlands dual group. You see, so you have these commuting operators acting on the Hilbert space. So naturally, we want to describe the spectrum, the joint spectrum of these commuting Hecke operators. That's what you get on the automorphic side. And then you also have the Galois side. That's the Galois side. Which has to do with this homomorphisms from the Galois group of the closure of F to the Langlands dual group, you see. And so the point is that such a homomorphism also gives rise to some data. And the idea is that the joint eigenvalues of the Hecke operators can be encoded by a specific homomorphism from the Galois group. Namely, the Hecke eigenvalues are the images under the so-called Frobenius conjugate classes. This works very well for GLN. And in fact, in this case, it's a theorem. For general groups, there are many subtleties which I'm going to kind of sweep under the rug for the purpose of this talk. They're not essential. But I hope I give you sort of a general idea of what this correspondence looks like in the case of curves over finite field. Crucial here is the possibility of defining a measure. So the space in question is or the set in question, the double quotient, is the set of equivalence classes of G bundles. And this set is nice in the case of a curve over finite field. It's a discrete countable set with a natural measure. We use that measure to define a Hilbert space. Then we define Hecke operator. The conjecture is that it can be described in terms of data on the Galois side. That's the case of a curve over a finite field. Now, if the curve is over a field of complex numbers, that is to say, we have a compact Riemann surface. Yes, in this case, we also have this double quotient, which can also be identified with the set of principal G bundles on this curve, right? But now it is not possible. There's no natural way to define an integration measure on it, it turns out, in the way we did for a curve over a finite field. Because now, for instance, the groups of automorphisms are infinite, and most of them are infinite. So it's kind of doesn't make sense. For this reason, the Langlands correspondence, people were puzzled when they first encountered this. How do you formulate the Langlands correspondence in the third column of the André Weiss Rosetta Stone, curves over C? There's no obvious formulation in terms of defining Hilbert space, defining Hecke operators, and so on. It's not clear. So there was a very clever idea to do it in a different way, which is essentially due to Drinfeld, Lamont, Balançon, and actually I should mention Pierre Deligne also. He did something that motivated Drinfeld in the first place. And the idea was to switch from functions to sheaves. You see, from function to sheaves. In the first two columns, we have a nice sort of old-fashioned formulation in terms of functions. But in the third formulation, people thought it was not possible to do it. So instead, they went in a different direction and tried to formulate things in terms of sheaves. Now, it was not a random decision, because actually in the second column of the Rosetta Stone, when you have curves over a finite field, it is also possible to formulate things in terms of sheaves. And that's because of a great insight of Alexander Grothendieck, who explained to us a long time ago that if you have an algebraic variety over finite fields, then a certain category of sheaves, the so-called analytic sheaves, has a nice property that to such a sheaf you can associate a function. Basically, because you can take traces of Frobenius on the stalks of the sheaves, Frobenius automorphisms, and this gives you a number, and so you get a function. So in the second column, both formulations are possible, and that's what led these people to the insight that you can try to forgo functions in the third domain, in the third column of the Rosetta Stone, and just formulate everything in terms of sheaves. This formulation is referred to as geometric or categorical in terms of sheaves. So what happens here? On the automorphic side, if there are functions, you can see the derived category of sheaves. What kind of sheaves? More specifically, so-called D modules. That is to say, modules over the sheaf of differential operators. That's not essential right now. What is important is that they are not functions, they are sheaves. And I will explain in a moment why this is natural. Instead of Hecke operators, you consider Hecke functors. You see, so this is what it's an example of what becomes a very fashionable idea in mathematics in the last, I would say, maybe 20 years. So-called categorification, where you replace sets with categories, functions with objects of categories, and operators acting on vector spaces with functors acting on categories, and so on. This, by the way, also makes sense in physics, and in the Kapustin-Witten formulation, they also consider categories. On this side, there will be categories so-called A-branes, also very fashionable in quantum physics these days to consider categories of branes. These are specifically what's called A-brane on the Hitchin moduli space associated to the group G with respect to some specific symplectic form. And you have so-called Hooft line operators, which act as functors on this category. So that's on the automorphic side. What about the Langlands dual side, the Galois side? Then we consider the category of coherent sheaves on the what's called moduli stack of flat LG bundles. And that also has a physics counterpart according to Kapustin-Witten, category of B branes. Anyway, there's many terms on this slide. So if you're not familiar with them, don't worry about it. It's not essential for this talk. This is maybe more for experts who have already been exposed to this material, just to connect it to what I've been saying. The bottom line is the formulation is categorical and geometric, you see, and not function theoretic. We are not constructing Hilbert spaces. We're not constructing operators. We're not constructing eigenfunctions. Instead, we consider a category of sheaves on the same object, by the way, this band G, but a category now, with band G being viewed as an algebraic stack or something that has to do with algebraic geometry. And instead of operators, we consider functors. And instead of eigenfunctions, we consider quote unquote eigensheaves, you see. So you get this categorical correspondence, which actually can, in the abelian case, if the group G is abelian, is what's known as Fourier-Mukai transform. So it's something in abelian case, it's something rather well understood in algebraic geometry. Now, this point of view, and when I say this point of view, I mean the idea that instead of in the third column of the Langlands correspondence, unlike the first two, you don't do things in a function theoretic realm. You don't try to construct a Hilbert space. You don't try to construct operators on this Hilbert space. You don't try to construct eigenfunctions of these operators and then link it to something on the Galois side. No, instead, you consider a category of sheaves. You consider functors acting on this category, and you consider sort of eigenobjects of these functors, which can be defined in a rather straightforward fashion. And then you want to link those to objects on the Galois side. This point of view has been the prevailing wisdom in the subject for the past 30 years. And it, for instance, I never thought that it was possible to do it in any other way. And yet, in our recent joint work with Etingof and Kazhdan, we have shown that there exists actually a function theoretic version as well. So for curves over complex numbers, there are two versions. There is a geometric categorical version, which has been developed in the past 30 years, starting with the works of Deligne, Drinfeld, Lamont, Bellinson, and so on. But there is also a function theoretic version. We call it analytic version. And the two are not in contradiction, categorical and analytic versions. They actually complement each other. And we can use each of them to gain insights about the other. In fact, for those familiar with two-dimensional conformal field theory, this state of affairs is not at all surprising. In the two-dimensional conformal field theory, we have correlation functions of two kinds. Conformal field theory means that it is a theory which has invariance under a group of conformal transformations, which are essentially holomorphic functions, right? So correlation functions, there are physical correlation functions. Now, the functions on what? So the functions on the parameters of the theory. And the parameters of the theory are, the theory can be defined on any Riemann surface, actually Riemann surface with punctures. So the parameters of the theory are, could be, it's a Riemann surface X and a collection of points on it, right? These are the parameters. So correlation function, or partition function, whatever, is going to be a function of these parameters. For instance, if X is just the projective line, then the parameters are just the positions of the points. And the honest to goodness physical correlation function is going to be a single value function of these parameters, not holomorphic, not anti-holomorphic, but some smooth function, say, C infinity function. But on the other hand, we also have conformal blocks, what's called conformal blocks and anti-conformal blocks. Those are holomorphic and anti-holomorphic functions, or maybe sections of some line bundles on this data, on the modular of this data. So what's the connection between the two? The connection is quite clear. This one can be written as a bilinear combination. So with some coefficients, let's say A alpha beta, and then you have conformal block and anti-conformal block, you see. So actually maybe better to say sesquilinear combination. It is, of course, a well-known fact that oftentimes you may have some finite dimensional space of holomorphic sections of a line bundle, which have monodromies as you go around various divisors, and you also have the anti-holomorphic ones, But you can create, sometimes you can create a single valued expression. In other words, one monodromy kind of kills the other monodromy so that you end up with a single valued object. So this is a state of affairs in two-dimensional conformal field theory. There exist both. So that there are holomorphic things, which are sections of some vector bundle with some non-trivial monodromy, and they're holomorphic. Likewise, there are anti-holomorphic counterparts. But these are not the true physical correlation functions. The true physical correlation functions, of course, are single valued. How to get them? Well, you have to take a bilinear combination. This is almost exactly what happens here. Basically, the geometric story gives you conformal blocks. Geometric story gives you analogs of conformal blocks. And the analytic Langlands correspondence is about the single valued physical correlation functions. Okay. So now I want to finally get to the subject itself, to the analytic Langlands correspondence proper. That's the functional theoretic version in the third column of the Rosetta Stone, when you have curves over a complex field, but not the traditional one, which would be like the story of conformal blocks, and therefore is geometric. So it has to do with categories and so on. That was on this slide. Did I? Oh yes. So I guess I jumped over one slide. So we have actually identified. So in contrast to the traditional story, where you can say categories and so on, we actually define a natural Hilbert space, and Hecke operators, analogs of Hecke operators acting on it. But actually, initially, there's some difficulties compared to the standard theory for curves over finite field. They are initially defined on a dense subspace. And we conjecture that, they can be extended to bounded operators on the entire Hilbert space. And moreover, these operators are commuting normal and compact operators. So they have a very nice spectral theory. You can describe it turns out that all joint eigenspaces are finite dimensional. And this operator, but there is more. So actually this can be done when a curve is defined not only over the field of complex numbers, but when the curve is over any local field. So it could be also real field of real numbers, or field of p-adic numbers, or extensions of fields of p-adic numbers. But in the case when the field is a field of complex numbers, and also to some extent when the field is a field of real numbers, there is more, because there are also differential operators which act on the Hilbert space. They're going to be unbounded operators, but they're going to commute with the Hecke operators as well. Those operators actually have been known since the work of influential work of Beilinson and Drimfeld from the early 90s on quantization of Hitchin systems. But they consider just the holomorphic operators. However, we also have anti-holomorphic ones, and actually both of them are important in the story. With Etingof and Kazhdan, we conjecture that the joint spectrum of this commutative algebra of Hecke operators as well as differential operators can be identified with some data on the other side, with some data related to Langlands dual group. So you see how interesting. The Langlands dual group again appears. So it's a persistent phenomenon throughout all the columns of the Langlands correspondence. And operas are particular bundles with connection. But the the interesting aspect is that only those appear here whose monodromy is in a split real form. So for instance, if the group is GLN it's of C, we insist that the monodromy should be in GLN of R, and so on, or SLN of C, SLN of R, and so on, the split real form. So these are the Galois parameters. So indeed, again, you have a correspondence between automorphic data, these eigenfunctions or joint eigenvalues of this commutative algebra of Hecke operators augmented by differential operators, and some geometric data, kind of Galois data related to the Langlands dual group. That's what we mean by the analytic Langlands correspondence. And this actually has some applications to mathematical physics, because the spectral problem for these operators can be viewed as a quantum integrable system. So let me see how much of this I can explain. So on this slide, I basically have the setup, but let's not worry about this too much. So this only there is a natural extension of the theory where, in addition to a Riemann surface, that is to say, projective curve over complex numbers, you also have a point. You have some punctures. So it's not just the Riemann surface, but a collection of points, a finite subset. And instead of bundles, just bundles, G bundles, principal G bundles, you consider more refined data involving these points. You consider pairs, a bundle on X, and reductions of this bundle to the Borel subgroup at these points. So then there is a certain open dense subset, and there is a crucial assumption that we have to make for things to be well defined, is that this open dense subset is, this subset is open and dense, which means that the genus of X is greater than 1, or it's equal to 1, but then at least 1 point is required, or it is 0, but then at least 3 points are required. And then in that case, you have this nice open dense subset, which for all intents and purposes can be replaced by the corresponding what's called coarse moduli space, which is a smooth algebraic variety, although non-compact, but smooth algebraic variety. Once you have a smooth algebraic variety, you can define a Hilbert space of now how to do it. So you see, you cannot take functions, because in principle you could take functions, but then you need some measure because you want to define an inner product. So how do you define inner product? You want to take the product of one function, say, and the complex conjugate of the other, and integrate. If you had a natural measure, you could do it. But the idea here is, and of course it's very familiar to us from quantum mechanics, that the right thing to do is to take not functions, but half densities. You see, so that half densities is denoted omega 1/2. There is a line bundle, a well-defined line bundle of half densities. And that is what saved the day, because we define the structure of a Hilbert space not on functions, but on half densities. If you have two half densities, then this product is going to be a density. And so you integrate it without making any choices, because it's a density, you see. So you start with completely supported ones, of course, then this integral is well defined, and then you take a Hilbert space completion. That's your Hilbert space. I hope it's clear. So it's very familiar for quantum mechanics. You have a certain manifold, and you consider the space of square integrable half densities on it. That's our Hilbert space in this case, in the analytic Langlands correspondence for complex curves. So now what kind of operators can we have on this? So they're homomorphic differential operators, obviously, but they're going to be unbounded as always, because you see, even in the simplest case, say you do harmonic analysis on a circle, so you have your harmonics, and this is the basis of your Hilbert space. But when you differentiate harmonics, sign of nx, the n pops out. So if you have a square integrable function, so then the sum of squares of the coefficients when the Fourier expansion has to converge. But when you take the derivative, it may not converge because you have multiplied each coefficient by n. That's why it's an unbounded operator. And the same thing happens here. So differential operators are singular. They're kind of difficult. They're easy to construct, but they are difficult from the point of view of functional analysis, because even to set up a problem, a spectral problem, you need to do some work. You have to find their self-adjoint extensions and so on. You see, even if they're symmetric operators on a certain dense subspace. They're also anti-holomorphic differential operators, plagued by the same problems. And then there are integral operators, which are much nicer because integration improves convergence, doesn't make it worse. So differential operators are difficult, as I just said, but they're nice because in some sense they indicate it's easier to understand what their eigenvalues are if we can set up the corresponding spectral problem. Heck operators are also initially defined on a dense subspace, but in that case, we believe that we conjecture and prove in many cases that they can actually extend to bounded operators, which are moreover normal, compact, and have the joint the space of joint kernel of this operator is finite dimensional. So you get a very nice spectral problem. And so then when you put these two together, you get sort of the ideal situation that on the one hand, those integral operators give you a nice spectral problem. On the other hand, the differential operators tell you what the eigenvalues are. So that's basically the situation. So now, next I was going to talk about holomorphic differential operators. And here we have a very nice, very good understanding of the structure of holomorphic differential operators acting on these half forms. there's a theorem of balancing and Drinfeld that they can be, the algebra of these operators can be identified with functions on a certain space, which is called space of operators. I already mentioned operators earlier, so I just want to indicate what these are. And perhaps the best way to do it is just to look at the special case when G is SL2, and then the dual group is PGL2. In this case, an operator is just what is known as a projective connection, a kind of a Sturm-Liouville operator, second order operator with symbol 1 and principal symbol 1 and subprincipal symbol 0, acting from -1/2 forms to 3/2 forms. If you have an operator like this, it makes sense to talk about its subprincipal term, and it has to vanish. So it's like d squared minus v. These are the operators in this case. These are the geometric objects which replace Galois representations. I feel that I have very little time left, so I'm going to jump over a few steps. I was going to, if I had more time, I would tell you a story which is very dear to my heart because it has to do with some work which I did in my first 2 years at Harvard on the invitation of Arthur. In fact, I came in September, as I mentioned, of 1989. That was a time of great turmoil, by the way. That barely a month later, the Berlin Wall came down, and the world became very different. But in the spring semester, in January, another visitor came to Harvard, also invited by Arthur and the math department, none other than Vladimir Drinfeld himself. So this was 1990, just before he received his Fields Medal for his spectacular work on Langlands program that some of it I just mentioned earlier. And just at that time with Fagin, I was studying the representations of affine Kac-Moody algebras. And it turned out that this work was relevant to Drinfeld's project that he was working at the time, which eventually he joined forces with Sasha Bellinson, and they wrote this spectacular paper on quantization of Hitchin systems a few years later. And so this is how I first learned about the Langlands program, because Drinfeld came, and so I would come to the math department at Science Center, and I would, knock on his door and ask him what he's working on. And he said, actually, what I'm working on is related to your work, because I know from Fagin that these are the results that you have obtained, and they are relevant to the Langlands program. So then I became curious what Langlands program is about. And so he was teaching me what this is and giving the reference and so on. So this is how I entered the subject. This is all happening in where most of you are, in Cambridge, Massachusetts. It's specifically the Science Center, on the math department. And so that's why I kind of wanted to include all of this, the explanation how this result that is crucial here by Bellinson and Drinfeld, describing holomorphic differential operators on band G. It comes from the study of affine Kac-Moody algebras and the corresponding chiral or vertex algebra. So it's actually closely connected to the two-dimensional conformal field theory, kind of very much like. And so that, for instance, there is this, there is a center of this Kac-Moody algebra at the critical level. There are the Shugawara currents, which play a big role. I'm kind of going to just leaf through. I suppose I could make the slides available for those who are interested, and maybe on the website of the seminar or something like that. So those who are interested will be able to view them later. But I don't want to take too much time on this. So basically, there is a certain local to global correspondence, which links the representations of Kac-Moody algebras. On the one hand, that's a local story to holomorphic differential operators on band G. That's a global story. And so then you can consider the eigen problem for this holomorphic differential operators, right? So let's suppose, so the algebra of holomorphic differential operators is really just the algebra of polynomials in n variables, where n is basically given by this is called quantum Hitchin system. And the eigenvalues could be nicely encapsulated by what's called the operator for the Langlands dual group. Now, and this is a crucial point, which more or less I probably have to end with this. The crucial point, and this connects nicely to what I said earlier about conformal blocks and physical correlation functions. The problem with the system is that solutions, there are holomorphic, locally holomorphic solutions, but they have monodromies because the space on which they're defined is non-compact. So there is a divisor at infinity. And when you go around the components of that divisor, you're going to get monodromies. So there are finite dimensional space of solutions which give rise to a vector bundle of very high rank, I might add, which grows exponentially with the genus. But you cannot say that these other automorphic functions, because there isn't a single solution, they're all mixed, they get mixed up by the monodromy. You see, this was the reason why until recently, mathematicians talked about categorical approach. So the idea of balance on the input was that instead of trying to single out a specific solution, which is impossible because of monodromies, you just look at the system of equations itself, or the more elevated term for this is a D-module. D-module is basically just the system itself. So look at the system itself as an object of a certain category, and it turns out to be meaningful. That is the Heck eigenshift in the story, you see. So that's the story of geometric categorical Langlands. And what we are doing now is we are coupling this holomorphic system with the anti-holomorphic system, because there are also anti-holomorphic differential operators. So instead of considering just the eigenvalue problem, eigenfunction, eigenvalue problem for the holomorphic ones, you couple it to the corresponding system with anti-holomorphic operators. And so you get a combined system of equations, you see, like this, a kind of a double of the Hitchin system with both holomorphic and anti-holomorphic degrees of freedom. And then you can have single valued solutions, just like physical correlation functions, which are bilinear combinations of holomorphic solutions of the holomorphic system and anti-holomorphic system. And it turns out, so our conjecture is that these eigenfunctions actually give you a basis in the Hilbert space. And the eigenvalues themselves correspond to this opers with real monodromy, you see. So that's the analytic correspondence. And I hope that it shows you the connection between the categorical one and the categorical correspondence and the analytic correspondence. Now, this can be made very explicit. For instance, when the curve is a P1 and you have finitely many points, then you get what's called the Kazhdan system. So the special case of Hitchin system for this situation is called the Kazhdan system. And you can write down this operator very explicitly, and then corresponding double of the Kazhdan system. And then it becomes a very concrete statement that the system has a single valued solution in half densities, if and only if the eigenvalues combine the eigenvalues give rise to this second order Fuchsian differential operator. That's what the oper is in this case, with real monodromy representation, By the way, one of them is the Fuchsian operator, which gives rise to the uniformization, but there are many others as well with real monodromy. So I guess that's, and then I wanted to talk about the Heck operators, which kind of tie everything together. But since I only have 3 minutes left and you might have questions, it's probably a good place to stop. Thank you very much.
Thank you so much. This was absolutely beautiful introduction and talk. I'm going to stop your Sheen squaring so we can see each other. I have so many questions, but I think that it would be best if you come to Cambridge and spend a month here so we can discuss all of that. But
it's a prodigal child, a son coming back home.
So I hope that this will generate a great deal of discussion, and please turn on your video when you talk so that we can see each other. Well, if there are no comments, maybe I start with this question that confused me. You talked, Eddie, about certain extensions of operators, self-adjoint extensions, and I'm not sure which of the differential operators that you talked about at the end are going to be self-adjoint, but are any of them essentially self-adjoint where they're uniquely determined on their domain of definition?
So essentially, initially we have some dense subspace, right, in the Hilbert space.
Yes.
On which they are well defined.
And are the closures ever self-adjoint?
But just the closures on that domain are not self-adjoint usually. So we have to do an extension. So there's some kind of a Schwartz space, subspace, the kind of to which we have to extend.
Yes, and
Now,
the deficiency indices are always infinite or they're finite?
say again?
The deficiency indices are infinite or finite?
I think they're finite. I'm not. I think so. But it's very so. In our first work with Etingof and Kazhdan, we try to construct this self-adjoint extension by hand, so to speak. So kind of to guess it. You see, I think actually not now that I think about it, I think they're infinite. And so it's kind of difficult to get. So we guessed, and the guess actually proved to be correct later on in many scenarios, in many cases we consider. But in the original work, we could only prove it when you have, in the simplest possible case, when you have a Riemann surface is P1 and you only have 4 points. So that's like the simplest case. When the modular space is one-dimensional and so on. And even there, it was a lot of work. But then in our second paper, we were able to introduce these Hecke operators. And which, by the way, since I didn't show this slide, I want to say that there's some earlier work connected to this by Braverman Kazhdan, by Kontsevich, and by Langlands himself, which kind of served as a motivation. So, in other words, if you just stay with differential operators, then because they're unbounded and because this not self-adjoint initially, or even the closures are not even essentially self-adjoint, it's very difficult to prove anything. But what saves the day is the existence of these integral operators, the Hecke operators, which are bounded and moreover compact. Turns out that they are compact and normal. Well, self-adjoint. Obviously, you can once you have a bunch of normal operators, you construct a bunch of self-adjoint operators. And so then the spectral program for them is very nice. So it's commuting compact self-adjoint operators. Then you have a spectral decomposition where with finite dimensional eigenspaces, and moreover the common kernel is also finite dimensional. So you split your vector space into finite dimensional components, and each of them is preserved by the differential operators. So naturally, then things come together, and then you can easily define the Schwartz space on which of rapidly converging series of these eigenfunctions on which the differential operators are going to be essentially self-adjoint. You see, so that's the state of the art today. That we are helping the integral operators, the Hecke operators, are an essential component which help us to make the spectral problem for the differential operators well posed. But the drawback with integral operators is that it's not clear in what terms to describe their spectrum, because we have these commuting operators, but we cannot describe the algebra of these operators in any other terms. But differential operators, on the other hand, can be identified. The algebra of differential operators can be identified with the algebra of polynomial functions in a certain space called space of operators. So then naturally their eigenvalues are points in that space, and then we can pin down exactly which of those points arise as eigenvalues. These are the operators with real monodromy. So that's how these two type of operators, differential and integral, help each other.
So are there questions from other people?
Yeah.
Danjoy,
Yes, can you
want to
yeah,
say?
can you hear me? Yeah. I just was curious if there is some connection with the talk that Langlands gave during his Abel lecture and his famous Russian paper, that unfortunately people who don't read Russian cannot understand.
Right. So yeah, that's
is
right.
it connected with what he said during this lecture?
That's right, it is. And so in fact, I said earlier that this work, my joint work with Etingof and Kazhdan, was motivated by the work of Langlands, and I meant that work that you referred to. So in 2018, Langlands received the Abel Prize, and around the same time he released this manuscript in Russian, as you mentioned, right, on the website of the Institute for Advanced Study. And I was actually in Oslo for the ceremony, and I was asked to give a public lecture about Langlands program. But on the same day, Langlands also gave his Abel lecture, and he talked about this work. So then later that year, there was an Abel symposium in honor of Langlands in Minnesota, where I was asked to speak about Langlands' work, and that's sort of me trying to understand that work led to this joint work with Etingof and Kazhdan. So Langlands actually said that it should be possible to define Hecke operators. Now, in my opinion, he did not succeed in his work to do it because actually, in some sense, he chose the most difficult case because, as I said earlier, our results only work under certain assumption, and the assumption is that if your Riemann surface is of genus 0 or 1, you need to have some points in addition and some additional structures at those points. If the curve is of genus 0, you need at least 3 points, and if the curve is genus 1, then you have at least 1 point. You need at least 1 point. And Langlands wanted to consider the Riemann surface to be elliptic curve, but without points. So it's kind of it's the most difficult case in some sense. And so there are some difficulties in there, but ultimately, even though he did not succeed in constructing this operator, in my opinion, but his insight was correct. His prediction, his guess was correct that the Hecke operator should exist. And to his great credit, because it went against the majority opinion, so to speak. So 99% of people, maybe everybody except him, thought that it was impossible. Certainly, I thought it was impossible. And in fact, what happened was the kind of a history of this was that he in 2010, Langlands, Ngo Bao Chao and I wrote a paper together about punctoriality beyond endoscopy. And around that time, between 2008 and 2010, I spent maybe even earlier, I spent a lot of time discussing with Langlands, and he wanted to learn the geometric correspondence, and which is the categorical version, right? So with sheaves instead of functions. And I spent a lot of time trying to explain it to him, and I guess I did a very bad job because he was not very satisfied. So he kept saying, "I don't want sheaves, I want functions," you know. And so I thought, well, you know, excuse me, but it doesn't work. But then, because he was so insistent, I actually at some point I did understand that it's possible because of this analogy with two-dimensional conformal filter dimension. That the fact that you can actually construct single value functions by taking bilinear combinations, holomorphic and anti-holomorphic, just like you can do, you know, exponential of harmonic function can be written as exponential of holomorphic times exponential of anti-holomorphic. And I thought that maybe in this framework one can do it, but I was still doubtful that Hecke operators could be constructed. But Langlands was adamant that they should exist, and he was absolutely right. And it was, in some sense, our work vindicated his insight and his guess that we were able to indeed construct Hecke operators. In fact, some of that was actually done by Kontsevich earlier, but we didn't know in special cases, at least. And Braver and Kazhdan had some results for curves over periodic fields, which actually, in retrospect, we could have kind of started from that. But anyway, so that's the link to Langlands, that he was. He had an insight which went against the grain, so to speak, against the prevailing opinion. And in some sense, what we did is we proved him right, that there exists a functional theoretic version, the Analytic Langlands correspondence, in addition to the geometric one. And there exist all the ingredients, but analogs of the ingredients, including the Hecke operators.
Thank you.
So maybe I can ask us. I'm just wondering, in conformal field theory, you don't just pair half densities, or you could pair something to get some spinning, something with conformal weight. Do these play a role, and what would that role be if they do?
Well, yes. So this is a very special case because, in fact, so usually in conformal field theory, you have the conformal invariance, and then the parameters are basically Riemann surface complex structures and some punctures, complex structures on a pointed Riemann surface, right? And you're trying to construct your correlation functions as functions of those data, and they're going to be not functions usually, but sections of some line bundles, and this has to do with conformal anomaly and so on. Now, what we have here, strictly speaking, is not a conformal field theory because we are considering a very strange case where you have a Kac-Moody symmetry, so kind of a gauge symmetry, but at what's called the critical level. And that's exactly the level at which the Shugawara operators become commutative. So away from the critical level, for example, if your level is positive integral, which is where you have WZW model, then you have the stress tensor, which you can construct as bilinear current, which I wrote actually formula, Shugawara current. If the level is non-critical, so critical means minus dual Coxeter number, it's negative, first of all, negative integer. If the level, for example, is positive integer, you have a stress tensor which generates conformal symmetries, and then you can do everything in the usual way on the moduli space of pointed even surfaces. But now, in addition, you also have Kac-Moody symmetry, so you can also have additional degrees of freedom which have to do with G bundles. So G bundles here are kind of Kac-Moody counterparts of the moduli of Riemann surfaces, punctured Riemann surfaces, which correspond to conformal symmetry. Now, at the critical level, you lose conformal symmetry. You don't have conformal invariance anymore. So you cannot move along complex structures because there is no stress tensor. But the gauge symmetry remains. So you can do things on the modular bundles on a fixed Riemann surface. But then instead of conformal anomaly, so of course there's Kac-Moody anomaly too. But in this case, this Kac-Moody anomaly is precisely half densities. It gives you half density. The line bundle is a bundle of half density. So it is kind of forced upon us precisely at the critical level. That line bundle is precisely the analog of the line bundle corresponding to conformal anomaly in the usual conformal field.
Thank you.
Are there other comments? So Eddie, you talked about a great deal ideas from physics and conformal field theory coming into mathematics. Are there any ideas that go in the other direction that imply new things from the point of view of physics?
Oh yes, so I mentioned that the work by Kapus and Witten from 2006. So actually the S-dual, it was known, it was kind of understood already for a long time that there must be some link between four-dimensional supersymmetric gauge theory and electromagnetic duality in it and Langlands correspondence. Now, why? Because the electromagnetic duality for non-abelian gauge theories was discovered in the late 70s in the work of Monton and Olive, and also Goddard, Knights and Olive. And they understood back then in the late 70s that if you have electric and magnetic operators, line operators, you have Hooft operators, Wilson operators in common terminology. But the charges are correspond in one case correspond to group G, but for the electric, but for the magnetic you get, it's not a group G because there is a switch between the lattice of weights and co-weights, and the co-weights of the group G are the weights of another group. So they actually introduced the Langlands dual group around 1978, physicists did, that I mentioned, the names I just mentioned, without knowing about the work of Langlands. And in hindsight, this is exactly the same group, more precisely the compact form of the corresponding Langlands duality at the level of compact forms rather than complex Lie groups. So Ed Witten actually says that back then it was Michael Atiyah who noticed that connection and alerted Witten to that. He said, look, these groups that these guys, Monton and Olive and so on, and Goddard, Knights and Olive are getting in the electromagnetic duality of supersymmetric gauge theories is exactly the Langlands dual group. Why is that? And so Witten was puzzled by this for many years. And so when I met him for the first time, I would say around 91 or something, 92 maybe, he was asking me about this. So this was a big puzzle. But then eventually we had this meeting at the Institute for Advanced Study in 2004. And Witten then with Kapustin were able to solve it. So this was an insight really coming from the geometric Langlands, from mathematical Langlands program to dualities. And the idea, the insight was that you should not try to do correlation functions, but instead you do branes, we say branes and B branes. I mentioned briefly in my talk. And so that was an insight that that the connection between A branes and B branes can be understood as a kind of analog of the geometric categorical Langlands correspondence in the third column of the Rosetta Stone. So you could say, well, so what? But actually that led to a lot of research. And eventually, I think it was this insight that eventually led people to what's called AGT conjecture, linking things in four-dimensional supersymmetric Young Mills and two-dimensional conformal field theories. So I would say that this is an example of where, for once, or a rare case where actually mathematical work influenced physicists. We know that in the last 30, 40 years or longer, it was physics physicist insights that influenced mathematicians, for instance, things connected to mirror symmetry and things like that, right? So that, or Gromov-Witten invariance and so on. So usually physicists come up with this astounding conjectures, counting, Riemann surfaces on the Calabi-Yaus and stuff like that. And then it is left to mathematicians to try to develop a rigorous formalism and prove them. But in this case, it actually went in the opposite direction. Namely, it was the insights of mathematicians, the Langlands program, that helped physicists to see things in a new way in their world. And something similar happened last year, that influenced by this joint work of Etingof, Kazhdan, and myself. David Gayotto and Edward Witten came up with some new works on the four-dimensional supersymmetric Young Mills, which kind of accommodate now or reflect this analytic Langlands correspondence instead of the categorical one.
So can you say anything more about that?
Well, they were, well, I guess that's probably be difficult, especially without a whiteboard or slides. Maybe for that subject for the next seminar, or maybe you can invite Gayotto or Witten to talk about it. I think that they probably do a better job than me.
Very good idea. Are there other comments or questions? Nobody else? Well, if not, I want to thank Eddie again for an absolutely beautiful talk. And
Thank you.
yes,
It was a pleasure.
and I welcome you back on Thursday morning for a special talk by David Ruel. Bye-bye. See you then. Bye-bye.
Bye-bye.